Hi, and welcome back to another video. In this video, we're going to talk about using Taylor series and performing like compositions with them. So in other words, taking some of those Maclaurin series that we're comfortable with at this point, sine of x, cosine of x, e to the x, and constructing a new series based on those types of those series that we already know how to construct. So in the previous video, you should have been exposed to the idea that we can construct a Taylor series or a Maclaurin series. They're kind of interchangeable when they're centered at zero, using a formula that involves the nth derivative times x to the n power all over n factorial. And if we shift the center, then it's the nth derivative at that center value, and then the quantity x minus the center to the nth power all over n factorial. So that formula is in the previous video, so if you haven't watched that yet, you might want to check it out. But I just want to start by taking a look at the Taylor series for e to the x. Now, this series is centered at 0, so we also refer to it as a Maclaurin series. And when we look at this, the idea is that if I take the e to the x equation here that's graphed in blue, and I construct the Taylor series using that formula that we have, the derivative of e to the x is e to the x forever, and at 0, e to the 0 will always be 1. And so we'll see here that our nth derivative that goes into our series will always just be 1 for this particular equation. Now, if I add terms, so right now I've got k equals 4, so I've got 5 terms, because remember, k starts at 0. And the more terms that I add, we can see that our Taylor series, or our Maclaurin series, lines up beautifully with that function e to the x. We say it converges to that function. However, if I want to shift my function, I want to talk about the difference between recentering a function or recentering a series versus composing a series. So when I recenter a series, what I'm doing is I'm reconstructing from scratch a brand new series. So let's switch over and take a moment to look at a series, look at this very series, and if we recenter it, what will the Taylor series look like? So here we have the Taylor series for e to the x, and we've repositioned the center. Now this is different than doing a composition because we're simply shifting where the series starts its alignment, where the center of the series is going to be what I like to call pinned to the function. So we're still graphing e to the x, but now this series looks a little bit different because if we reshift the center so that instead of being pinned at 0, 0, we are now being pinned at the point 3 e to the 3, e cubed, and that's going to be our center point. So think of it this way, the series is pinned at 3 instead of at 0. And so to construct this, we're going to use that Taylor series formula where we have to find the nth derivative at 3 for e to the x. So it's e cubed forever and a day. And then as we construct our series, it looks like what we see here on the screen. And notice you have this coefficient now that includes e cubed over that n factorial. And so we have to include that as part of our recentering. Now, as we construct this new Taylor series, I want us to understand that this is not a composition, this is a recentering. So let's go back to our graph. So looking at my graph, I'm going to turn off the original series that we centered at 0, so that's the red one, and I'm going to highlight this new one. So now we have created this purple function, and we'll back k all the way up. And notice now that I am now centered at 3, and this is e cubed, 20.08554. So that's our center now. And so this becomes the place where my function is pinned to e to the x. Notice I'm still graphing e to the x, but the difference here is now as I add terms to this new function, it still aligns with e to the x, but where it aligns from, that center where it aligns and then branches out, has shifted to where x is 3. So when we recenter a function, we have to reconstruct the Taylor series from scratch. So another great example of this that a lot of the time my students get confused about is when we talk about sine and cosine. We know that sine of x, the Maclaurin and Taylor series for sine of x includes all the odd powers when we're centered at 0. When we shift that center, all the even powers need to come back because the reason they disappeared in the first place was because sine goes back and forth between 0, 1, -1, and so on and so forth. So all those terms that were 0, those are no longer 0 because now we have to consider the sign of wherever we're centered at, not 0. So recentering a series is different than doing a composition. And so I want to get that distinction right out there and make sure you guys understand that when you recenter, you are still aligning to the original function of e to the x. We're just moving where we center. And so if we just put both of them on the screen here, just to get a better idea of what we're seeing. So here's the red and the blue is the original. So the red graph is pinned right there at 0. And as we move, you'll see that they both will align to e to the x. It's just a matter of where are they aligning from? What is the center point where these series, these infinitely long polynomials are being pinned? So now let's talk about what we do when we do a composition with a Taylor series. Now, this Taylor series here, f of x equals cosine of x, or cosine of 2x, we can construct a new series based on the Maclaurin series for cosine. So what I want us to kind of zoom in on here is I want us to think about these common Maclaurin series, and again, these are all centered at 0. That's a very important distinction. And I want us to think of them not as having x's floating around, but I like to think of it as using, we like to use u as a substitution. So I want us to think of it like this. We've got cosine of u, and that's going to be equal to 1 minus u squared over 2 factorial plus u to the 4th over 4 factorial, and so on and so forth. So we'll have those alternating terms, but I want you to think of the x's in these Taylor and Maclaurin series as u's. And so if we think of them as a u, like we do with our substitution, when we go over and look at what it is we're trying to do, this right here is going to be our u value. And so when we go to construct our series, we simply need to take cosine of u and put 2x in for u. So every single one of these u's is going to be replaced with a 2x. And when we do this, we need to make sure that we're using parentheses, because we're not just squaring the x, we're squaring the entire angle that is replacing u. And so cosine of 2x should look like this. We should have 1 minus, and then in parentheses, 2x squared over 2 factorial. And then in parentheses, 2x to the 4th over 4 factorial. You have to include these parentheses. And then in our nth term, we also have to include parentheses. So my nth term for the cosine, I'm going to have that alternating negative 1 to the n power. And then I would have u to the 2n over 2n factorial. That's what gives me my even terms. I'm going to do the same exact substitution. Negative 1 to the nth power. And then instead of u, I'm going to put 2x in to the 2n power all over 2n factorial. Now, I don't recommend ever simplifying these, simply because the only time you'll really need to be concerned with simplifying them is trying to match them with a solution in a multiple choice. But if you were going to simplify these, you would need to make sure that you put that exponent to both pieces inside the parentheses. So you'd have to rewrite it as 1 minus 4x squared over 2 factorial plus 16x to the 4th over 4 factorial, and so on and so forth. So make sure that you have parentheses around your 2x, and make sure if you are going to distribute that exponent and apply it to everything inside, make sure that you apply it to the constant that is with the x as well. So let's keep going. Let's talk about some more compositions. What if I wanted to write this Maclaurin series? Now, I'm going to look at this and I'm going to say, okay, which piece of this function does it appear that I know? And I see a sine. And so what I'm going to do is I'm going to think about what is the sine Maclaurin series. X minus, sorry, I guess I should be consistent. We'll use u. U minus u cubed over 3 factorial plus u to the 5th over 5 factorial, and so on and so forth. And then we've got our nth term, which is going to have that alternator, and then u to the 2n plus 1 over 2n plus 1 factorial. So we've got our series for sine, and I'm going to ignore the x squared. I'm going to deal with one piece at a time. I'm going to reconstruct the series with 3x in it. So it'll look like this. We'll have sine of 3x, and in parentheses always 3x minus 3x cubed over 3 factorial plus 3x to the 5th over 5 factorial. And I could keep on going. I'll do my nth term here. And so we get our Maclaurin series for sine of 3x. Now, I want you to recognize that when you construct a Maclaurin series, that this is an infinitely long polynomial. And if we had a polynomial with an x squared on the outside, we would simply distribute that x squared to everything inside. So the next step that we have to do is just that. If we're going to take and multiply sine of x cubed by x squared, then what we want to do is we want to take every single one of these terms and we want to multiply an x squared with it. Never, ever, ever put parentheses around a Taylor series and slap an x squared on the outside. You have to distribute to every term. So we're just literally, I'm going to go x squared, x squared, x squared, x squared. And unless this is a multiple choice situation, I'm just going to leave that x squared with every single term, making sure that I also include it in my nth term. If I am going to simplify this, I would need to remember to put the exponent to the 3 as well, and then I could combine my my x's. Now, you may run into a situation in multiple choice where you have to match the exponent. So remember, when you have something like x squared times x to the 5th, it's going to turn into an x to the 7th power. And then this term would have an x to the 5th power, and this term would have an x cubed. So make sure that you know how to simplify your exponents, because you'll need that to match it up on a multiple choice scenario. But for just constructing our series, this is sufficient. Let's take a look at this e to the x series. So when I'm constructing this series, I am going to take a look at what part of the series do I know a known series for, and that's going to be the e to the 2x. So I'm going to start by considering the e to the x formula, which is nice and easy. We got 1 plus x squared over 2 plus x cubed over 3 factorial plus all the way to the x to the n over n factorial. And just like I thought about sine and cosine as having u's, I can think of all these x's as being a u value. And then u, for my intent and purpose here, is going to be 2x. So I'm going to start by constructing the series for e to the 2x. 1 plus 2x plus 2x squared over 2, 2x cubed, 3 factorial, and then I'll have 2x to the n over n factorial. Now, whenever I have addition and subtraction, it's different than multiplication. So in the previous example, let me slide back up, we had an x squared and we were multiplying. And the reason why we multiplied x squared with every term is because we were literally taking a polynomial, an infinitely long polynomial, and distributing x squared because we were multiplying. I want you to think about if you have a polynomial, and in that polynomial you have addition and subtraction. So for example, if I have 2x squared plus 3x minus 4, and I want to subtract 1 from it, I'm not going to subtract 1 from every term. I'm going to combine my like terms and make that a minus 5. And so I'll have 2x squared plus 3x minus 5. So if I'm subtracting 1 from this Maclaurin series, I want to think about it the same way that I would that polynomial. So if I take e to the 2x, and if I go over here and we'll zoom in a little bit, kind of erase, and I make it e to the 2x minus 1, when I go to subtract 1, I'm literally taking this polynomial and subtracting 1. So I'm going to combine any like terms, and nice for me, this one and this one end up canceling out. So I end up getting this series, 2x plus 2x squared over 2 plus 2x cubed over 3 factorial, and nothing else changes. I simply lost that first term, that constant of 1. Now the last piece that I have to do, it says here that I'm dividing by 3. And so in the same way, if I were taking this polynomial and dividing by 3, I would do the same thing with every term. And so I would turn this into 2x squared over 3 plus 3x over 3 minus 5 over 3. I divide every term by 3. Well, in the same way, remember, I'm dealing with a polynomial, so polynomial rules all apply here. So if I need to divide by 3, then I am literally going to take every single term and divide it by 3. And when I do, I'm just going to leave it in the bottom as a multiplier. So 3 times 2, and then this becomes 3 times 3 factorial, and this becomes 3 times n factorial. So I'm literally just multiplying all the denominators by 3, and that achieves my result. And so this would then be the series for this function. And if I really wanted to, I could go to Desmos and I could graph both of these and check to make sure that they are exactly the same. And so here we have the function that we were trying to construct the series for. And if I look at the series as I add a term, lo and behold, we are centered right there at 0. And you can see that, yep, here's my nth term that we just came up with. This does, in fact, converge to that function. So you can always use Desmos, and all you need to do is graph your summation notation. Just start typing the word sum into Desmos and it pops up. Otherwise, you do have the little menu down here that gives you all kinds of functions. And this is where you can kind of find a lot of the things you might need, including other functions like for derivatives and integrals and things like that. And Desmos will do all the things you need it to do for your AP exam. And so I think this brings us to a good stopping point for this particular topic, doing constructions and compositions with Taylor series. You can also perform all the same things you can with a power series. You can do derivatives of Taylor series and things like that. So I'll be adding some additional videos that kind of dive a little bit more into some of the free response and some of the tougher types of questions involving Taylor series. So that'll be the next video in the series.